Now that we've learned all of these identities, we're going to look again at solving trig equations, something we've done since chapter 6, solving for theta, but now sometimes we're going to get an equation that has more than one trig function. So we're going to look at some strategies, how we can use our identities, how we can use our regular algebra skills to solve trig equations which may have more than one trig function in it. So the first part is just some strategies. Okay? If you can write an equation with only one trig function, and we've seen these ones before, where you have a sine squared and a cos, so you change the sine squared to 1 minus cos squared, then your entire equation just has cosine, and you're able to factor and solve. So we're going to see that sometimes we can change things to only one trig function. If we can do that, we'll be able to solve. And in brackets there, one trig function with just theta inside. Another strategy that's going to come up again that you've seen often is factoring. Maybe there's a common factor and you aren't able to change everything to just one trig function, but you can factor out a common factor. That might help us solve an equation. And the last strategy, which is very similar to strategies that we've used in proving identities, maybe you just change everything to sine and cos and see where it goes. So here's the first example that we're going to do. So in this first example, we have two different trig functions. We have cotangent and we have cos. So one of the strategies says, can you change everything to the same trig function? Is there a way to change cotangent to just cos? No. What can we change? We can change cotangent to 1 over tangent. We can change cotangent to cos over sine. So we can't use strategy 1 and get everything in the same trig function. There's nothing in common right now. So we're going to go to the last strategy here. We're going to change things to cos and sine. So cotangent is cos theta over sine theta equals 2 cos theta. And then it says eliminate any fractions. You want to get water. Wasn't it water that caused the problem? No? Okay. So we have cos theta over sine theta. How would I get rid of a fraction in an equation? Opposite of dividing? Multiplying. So I'm going to multiply both sides by sine theta. My equation then, these sine thetas would simplify, and I would get cos of theta equals 2 cos of theta sine theta. At this moment in the question, lots of students are very tempted to divide both sides by cos. Okay? Can you see if you divided both sides by cos, the coses would cancel out, and you'd be down to one trig function. And once you get down to one trig function, you can solve it. So it seems like a good strategy, but you will always miss out on some solutions if you do that. So I'm going to write here as a special note off to the side. That we want to factor instead of dividing, and we'll see why. Well, if I'm going to factor something, I need to make one side equal to 0, and then instead of dividing by cos, I have a common factor of cos that I can factor out. If you factor out that value, well, then either cos of theta is equal to 0, the first factor is equal to 0, or your second factor is equal to 0. Cos theta ever equal to 0 on your pie plate? Yes. When? When is your x-coordinate 0? Pi over 2 and 3 pi over 2. Sine theta ever equal to a half? Yes. Quadrant 1 and quadrant 2. Every time you finish solving a question, you should read it again, because we solved between 0 and 2 pi. Is that what the question asked for? Yes. Good. We don't have to do anything more. But we check our domain. It did say solve between 0 and 2 pi, and we did. Okay? If you divided both sides by cos, you would have got 1 equals 2 sine theta. Divide both sides by 2 to get sine theta by itself. You get sine theta is 1/2. On your pi plate, you would have got pi over 6 and 5 pi over 6. But you would have missed pi over 2 and 3 pi over 2. So we always factor, if there's a common thing that you could divide to get rid of, instead move everything over and factor instead. Because what's actually happening when you divide, since one of the solutions is cos theta equals 0, if you divide both sides, you are actually possibly dividing by 0, which is not allowed. And that's why you don't get the full solution, you just get a partial solution. So if you divided, you get some right answers, but you don't get the complete right answer as a result. So this is our first example of using identities to solve. Continuing. Sometimes we have questions with a 2x in it. Sometimes they're going to require an identity to solve, and sometimes they're going to require a multi-revolution question. We're going to look at both of those and determine which one is which. So, if you have a double angle in a solve question, sometimes you'll have only that trig function with a double angle. Then it can be solved as a multi-revolution question like we've already done. But sometimes you're going to have that double angle function and another trig function. Then you're going to need to use your double angle identity. Sometimes when you learn something new, it makes questions that you used to do harder because now you have more choices. So learning the double angle identities now make this question that we've done already on the left harder because you have a choice. You have a choice. I could change cos 2x to one of those three. Or I could leave it as cos 2x and solve as a double angle. So how do we know when to do which? Well, if you only have the double angle, like we do on the left-hand side, then solve it like a multi-revolution question. Move the root 3 over 2 to the other side. How do we solve multi-revolution questions? We first find our domain for 2x, twice around the circle. We then solve for 2x. When is cos root 3 over 2? Which family? Pi over 6 family. Which quadrants? Quadrant 1 and quadrant 4. That's your first time around. add 2 pi, that's your second time around. Then solve for x, divide everything by 2. And so we've solved our multi-revolution question like we've done in the past. Read it again. We've done it over the correct domain. So we're done. But the one on the right-hand side where it has sine 2x equals sine x, even though both sides have sine, we don't have the same trig function because one of them is a double angle identity and one of them isn't. And since we have a sine 2x and another function, this is a situation where we have to use an identity. So we change the sine 2x using our formula to 2 sine x cos x equals sine x. Can you see at this moment you might be tempted to divide both sides by sine x to get rid of it? So if you're tempted by that, right, we got to remember to factor instead. If we're going to factor, we need to move everything over to one side, and then instead of dividing by sine x, we can factor out a common factor of sine x instead. So we get sine x is equal to 0, and cos x is equal to a half. Are those on our pie plate? They are. When is sine equal to 0? The y-coordinate is 0 at 0 pi and 2 pi. When is cos x equal to a half? Pi over 3 family. Quadrant 1, it's positive, and quadrant 4, it's positive. Check your domain. Our domain was 0 to 2 pi, including both, so all of our answers are good. And finally, the last question that we're going to do together is example 4 back on page 657. Hey, no problem. So for question 4 here, we have a sine 2x. So we have to make a decision, are we going to use an identity, or are we going to solve it as a multi-revolution question? And since the question also has cos squared in the question, that tells us we have to use our identity. So I start by using the identity. I can change the sine 2x to 2 sine x cos x minus cos squared x equals 0. The 1/2 and the 2 cancel each other out. And we changed everything to sine and cos. We cannot change everything to the same trig function. You can change the cos squared to 1 minus sine squared, but you cannot change a cos to 1 minus sine, or a sine to 1 minus cos. It only changes if it's squared, if you're going to use the identity. So in this case, we're going to factor out a cos, because it's in common, leaving us with sine x minus cos x equals 0. And at least this part is easy to solve for. We know that cos x equals 0. The other part basically means that sine x has to equal cos x. So we'll do the easy part first. When is cos equal to 0? When is your x coordinate equal to 0? At pi over 2 and 3 pi over 2. And there's two ways that you can do the second part. One, you can think about your unit circle. Is sine x ever equal to cos x? Is your x coordinate and y coordinate ever the same? Yes. When? There's two places that it's the same. Pi over 4, they're both root 2 over 2, root 2 over 2. And 5 pi over 4 is when they're both negative. So you can do that one just by observation. The other thing you can do with this, in this case, you could divide both sides by cos. Your cos doesn't cancel out, so you haven't eliminated it to make it a problem like we've had with dividing in the past. And what can you change sine over cos to? Tan. When is tan equal to positive 1? Pi over 4 family, quadrant 1 and quadrant 3. You could have got pi over 4 and 5 pi over 4 that way as well. Okay. These solving ones are a big part of your exam because they're in Chapter 6 and they're in Chapter 7. Okay? As a result of them being in Chapter 6 and Chapter 7, the exam likes to put lots of questions on here. So I'm going to give you lots of questions for practice. And we've got a half an hour left. We're done this unit. The rest of class is for practice. Okay? On the back of your Identities worksheet was a bunch of solving questions. And that backside, which has solving questions, has a whole range of solving things directly to using identities. So there are some questions from that. So from the handout on the back, I will tell you the numbers that I'd like you to do. Okay, some of the numbers on the back of the page are circled. They have nothing to do with the homework assignment I'm giving you. So if you want to circle these ones or highlight these ones instead. 8, 9, 11, 12, 14, 15, 21, 27, 29, and 31. And then from your textbook, questions 12 to 15.